All right, today we're going to break down one of the most powerful tools out there for making sense of the world, the simple regression model. Seriously, this thing is the secret sauce behind headlines, big scientific studies, you name it. We're going to demystify how it takes a whole mess of data and boils it down to a single powerful number.
So you've probably heard this a million times, right? Go to school, get a better job, make more money. But how much more? I mean, how do we actually put a dollar amount on one more year of college? How can we get from just a vague idea to a concrete number? Well, that's exactly the kind of question we're tackling today.
Okay, section 1, drawing a line through data. To get at an answer, we've got to find a way to spot the main trend that's hiding in a huge, messy cloud of real-world data. We need to draw a line.
Just imagine for a second. We take the data for thousands of people, how many years of school they have, and what they make per hour, and we plot it all on a graph. You'd get this giant, messy cloud of dots, right? Regression is the magic wand we wave to draw one single, straight line right through the middle of all that chaos. It's the line that best sums up the whole story.
All right, section 2, the simple regression model. Now, let's get into the actual tool that statisticians use to find that line. And yeah, it might look a little mathy at first, but trust me, once we pull it apart, you'll see it's actually telling a pretty simple story. And here it is, the model itself. Don't let the symbols freak you out. Think of this equation as a little story with 4 main characters. Once you know who's who, you'll be able to read any simple regression you ever see. So first up, we've got y. This is our dependent variable. It's basically the mystery we're trying to solve, the thing we want to explain or predict. For our example, y is the hourly wage. Next, we have our prime suspect, x, the explanatory variable. This is the factor we think is causing the change in y. In our little detective story, x is the years of education. And now, for the star of the show, beta 1. This little guy is the whole reason we're here. This is the number we're after. It tells us exactly how much y changes when x changes by 1 unit. So, if we're talking about one more year of school, beta 1 is the number that tells us the predicted jump in your hourly wage. It's the magic number. But, life isn't that simple, right? The real world is messy. And that's where our last character, u, comes in. This is the error term. Think of it as our reality check. It represents literally everything else that could possibly affect wages that we haven't included in our model. It's all the stuff we don't know or can't measure.
So what kind of stuff are we talking about here? I mean, what's really hiding inside that u? For our wage example, it's not just random static. It's a person's innate ability, how hard they work, who they know, what they majored in, even just good old-fashioned luck. All of that stuff plays a huge role in what someone earns. Okay, section 3. Finding the best fit line. So we have our model, we know our characters, but with thousands of dots on our graph, how in the world do we pick the one line that's the absolute best fit?
Well, the method most people use is called ordinary least squares, or OLS for short. The best way to think about OLS is like a contest. It's trying to find the one line that gets as close as possible to all the data points at the same time. It does this by measuring the vertical distance from every single dot to the line, squaring that distance, and then adding them all up. The line that has the tiniest, smallest possible total score, that's our winner. That's the best fit line. So once we've found our winning line, we need a way to grade it. Like, how good is it really? That's where a number called r-squared comes in. R-squared tells us what percentage of the puzzle our one factor, x, actually explains. Is years of education explaining, say, 5% of why wages are different, or is it explaining 95%? R-squared gives us that score, from 0 to 100%. Section 4, correlation versus causation. Okay, so we can find a line, we can even score how well it fits, but here comes the big one, the multi-million-dollar question. Does that line actually show us that one thing causes another, or are they just happening at the same time? This is a whole other can of worms. Okay, listen up, because if you only remember one thing from this whole explainer, make it this. There is a huge catch. This is the critical idea you need to understand before you believe any regression result you read about, whether it's in the news or a fancy study. Just because two things are correlated, it does not mean one causes the other. So, for us to say our beta 1 number is a real causal effect, there's one massive rule we have to follow. It has a fancy name, the zero conditional mean assumption, but the idea is simple.
It means our main suspect X cannot be secretly in cahoots with all that other stuff we shoved into the U error term. They have to be completely unrelated, on average. Let's bring this back to our education and wage example. So, innate ability is one of those things hiding in our error term U. Now, in a perfect world, the average ability would be the same no matter how much education someone has. That's the good scenario. But what if the bad scenario is true? What if people who are naturally smarter tend to get more education anyway? If that's the case, our model gets confused. It sees more school and more money together, and it gives all the credit to the school when really a chunk of that effect is just raw talent. All right, section 5, regression in the real world. Now that we've got that huge warning about causation in our back pocket, let's look at how this all works with a couple of real examples. So, example number 1, a study looked at 209 CEOs to see if their pay was connected to how well their company was doing. They measured company performance using return on equity, or ROE. And the result? The regression model predicted that for every 1-point bump in a firm's ROE, the CEO's salary went up by about $18,500. Sounds interesting, right? But then they looked at the R-squared, and it was just 1.3%. Let that sink in. What that means is that how well the company performed explained almost nothing about the differences in CEO pay. There's a whopping 98.7% of the story that's completely missing from this model. But hold on, this is a really important lesson. A super low R-squared doesn't necessarily mean the whole thing is garbage. As the researchers point out, it's totally possible that the $18,000 number is a pretty good estimate of the specific impact of company performance on pay. It's just that company performance is a teeny tiny piece of a much, much bigger pie when it comes to CEO salaries. Okay, now for a totally different kind of example. This was a true experiment. A group of men were randomly assigned to either get job training or be in a control group that didn't. And the regression found that on average, the guys who got the training earned $1,790 more the following year. Now see, because of that random assignment, we can be way more confident that this is a real causal effect. That's the magic of randomization. It ensures that all that other stuff, the things in the U term, like motivation, natural ability, luck, it all gets averaged out between the two groups. It's the best way we have to solve that tricky correlation versus causation problem. So, the simple regression model. It's an incredibly powerful lens for looking at the world. But more than just giving us answers, it forces us to ask much smarter, tougher questions about what's really going on beneath the surface. It helps us separate a real story from a convenient one. And it really makes you wonder, doesn't it? How many of the things we just accept as true every day are real cause and effect? And how many are just correlations, waiting for someone to take a closer look?